All attendees are in listen-only mode.
Hello, welcome everybody to part 3 of Hydronics. This is Hot Rod coming at you from Missouri today. Today we're going to go into part 3 of what we call Hydronics, and we're going to talk about load side design. We've had previous webinars on the geo topic that John Siegenthaler helped us kick off. We talked about the basics of how geosystems work and the source side, the piping for the loop fields and the wells and different ways of doing that. Well, today we're going to focus on the load side, that being the emitters, different piping schematics. I'm going to show you different types of system drawings and wiring and piping schematics. So I think this is going to be the key to it. Now, this is all based on Hydronics number 9, which you should, by the way, have. It was mailed out last week. If not, keep an eye out for that. It is available on our website now also, so if you do want to download that as a PDF, it's up there as of yesterday. So a lot to cover as usual. I think we can pull it off here in an hour, so I'm going to start rolling along. Oh, I just got back from Alaska last week. I had a trip up there for 2 weeks. I spent a week up there with our reps with Mechanical Systems. I want to say a big thanks to the guys up there, Glenn and Jason and Amy and Mike, that made that a wonderful trip for me. I learned a lot about the market up in Alaska as well as a lot about Alaska, so thanks, guys. This was a picture one day that we hiked up to the exit glacier outside of Seward, Alaska there, and saw some mountain goats up there and had a great time. So also got to visit some great engineers up there. We visited some job sites. We looked at the Weller School project, which we'll talk about a little bit later, where they've got some solar interface with their geo loop field. That was really interesting. That's just coming online. And visited with some contractors up there in Soldotna, met John and Nathan, and some folks came up from Homer. Steve came up from Homer, so it was a great trip. I highly recommend Alaska. If you haven't been there, put that on your list of places to visit in your lifetime, because we had a wonderful time. The people were great. We even had some blue skies when we were up there. So, all right, moving along. Hydronics number 9. It's another fat issue, which is good news. I mean, there's a lot of information in there. There's a lot to know and learn about geo and how you interface it with hydronic systems and stuff. So keep an eye out for that copy. If you're not getting them in the mail, go there and register. You see, we put up our website there, caleffi.us. You can go there if for some reason you've fallen off our list and you aren't getting these mailed to you. You can get back on the list and you'll get one every time it comes out. As usual, it's pre-punched. Put them in the binder, save them. There's certainly a collector's piece. Most of the slides that I'm going to talk about today are going to come out of Hydronics 9 because, again, we're going to roll through this pretty quickly here. We've got a lot to cover, but if you want to go back and review what we talked about, you'll be able to follow through this. What I did is I started about in the middle of the book, probably about page 36, because that's where we started talking about the distribution side, the load side of it. So to follow along, if you have that issue, that's where I'll be starting. If not, look it up and you can follow through. Yeah, so that's what we've got online now. You can see we've got hydronics issues from 1 to 9 are archived down the line there. Of course, this webinar will be archived. It usually takes us a few days, probably next week sometime. You'll have this up on the website as an archive also. So if you have some of your staff or you want to review it and watch it again, it'll be posted there next week sometime. I want to put another plug in for John Siegenthaler. He helps us a lot with these webinars and with our hydronics issues, and he's got the 3rd edition of his modern hydronics out right now. It's a full color issue. It's been updated, upgraded. It's a much thicker issue than the first one, so if you don't have it, I would highly recommend that. You know, I've searched the world for information on hydronic systems and geo and solar as I've been working with Caleffi, and I've not found a better publication to cover all the aspects of it. It does have a good geo section in it also, and it also talks about solar and the interface, so grab one of those when you have a chance. All right, as we start talking about load side, what we want to do with the geosystem, and what you're going to notice here today is a lot of the things that we're talking about today are very similar to what we talked about in the solar presentations that we did. That being, we want to look for a distribution side or emitters that work at a low temperature, because the lower the temperature on the heating mode that we can operate the geo at, the more efficient it's going to be, the higher the COP. And the same thing was true when we talked about solar. The lower temperatures that you can run up to the solar collector, the higher the performance, the higher the efficiency. So with that in mind, we want to look for some systems that can operate at low water temperatures. And when I talk about low water temperatures today, I'm thinking maybe below 120 degrees F. What's interesting now is there's some products coming out on the market that can work at those temperatures and give you pretty good outputs. Probably the most familiar one to most of us here would be a radiant floor slab. Typically a concrete slab, that would be an excellent application. Those can run down at those temperatures that we're talking about, below 120 degrees. What we're finding is radiant slabs aren't always the ideal application for heating a home. If you're in a climate like I am here in Missouri where we have a shoulder season, we don't want to rev up our slabs quite yet because it's just a little chilly in the morning, but it gets warm during the day. We might want to look at putting some maybe backup system in there, maybe some little panel radiators or fin tube emitters or something like that. Well, up until recently, all we really had was the basic stuff that was really designed to be used at high temperature systems. Originally, when fin tube baseboard came out, it was designed to work on boilers in 180, 200 degree operating range. Didn't get much output of performance from that when we started talking about the lower temperatures, but there are some products and manufacturers that are addressing that market right now, and one of them is this company called Yaga, is how it's pronounced, I think. That's right. And they've developed a low temperature radiator system, which can be used to supplement a radiant floor system. So now you can run the radiators on the same temperature that you're sending out to the radiant slab zone. So that makes it pretty nice for zoning and for combining the two systems together. That I thought was a nice little cutaway of what they're explaining here. You can see on the right side, you can see the radiant floor slab and how they've got the radiators in these various rooms for supplemental heat or for the shoulder season heat emitters. Now, one thing that you want to look at, this was a great little graph that John put together, I should say. And what it does is it shows you the different outputs with different things that you can play around with when you start looking at doing a radiant slab, whether it's a new home or you're going to do a retrofit or a remodel project and you're thinking about doing a radiant slab. What we did here is we took a typical concrete 4-inch slab, and we wanted to show you how the heat output changes and how it varies based on the supply temperature here across the bottom, as well as the tube spacing. So over here on the left-hand side, you've got the amount of heat output. We'll call that the upward heat flux. That's the amount of BTUs per square foot that you can expect out of the slab. The different color lines here across the graph here show you the tube spacing at 6-inch, the blue colored lines, and then 12-inch on center. Then these numbers here are indicating what the floor covering resistance value would be. So obviously a bare concrete slab would have no resistance covering on it. Certainly that could be a painted or a stained slab. It wouldn't have to be just, bare gray concrete if you want to do a job that you want to zip it up a little bit and put some coloring in it or stain it or stamp it or something like that. But basically it's a slab that's not going to have any carpet on it or hardwood on it or vinyl, any kind of covering on it. And then as we go across the list here, you can see we're adding a little bit of floor covering on it. Maybe that's a piece of vinyl or a very thin, maybe 1/8-inch carpet or something like that. Getting over here in this R1.0, that would probably be, maybe a 3/4 hardwood that's put over a concrete slab or a carpet and pad. And then, of course, it goes up and up as you put thicker carpet and thicker pad or wool carpet and stuff on, the resistance starts to go up. But what I want to show you on this example right here is we took a typical job with a 20 BTU per square foot load. Now, that number may sound low, but nowadays with the homes being built with better construction, tighter windows, better insulation, thicker insulation, contractors and builders paying more attention to energy conservation. We're seeing these loads come in. Actually, I'm seeing some loads below 20 BTUs per square foot, even in cold climates. So that's a realistic number. We didn't try and pull that down on the graph just to show up the graph here. That is a realistic number that you might see in a modern home or remodel project. So we said, okay, let's look at a job where we've got a 20 BTU per square foot load at design conditions. What could we do to be able to run that off a geo system or a solar and geo combined system? Well, one of the things that we noticed right away is tighten up the tube spacing. So what we did here is we looked at this at a 6-inch on-center tube spacing. So this little formula right here is the temperature of the room and the temperature of the water that's driving the system. So the room air temperature based against the water supply temperature to the zone. So let's say we wanted to maintain the room at a 70 degrees. That's a typical design temperature, 70-degree indoor design temperature. To get 20 BTUs per square foot, we would need, come down to the bottom of the graph here, follow that down on the 6-inch center line, and you'll see we need about 17.5 is what that number is. Delta T difference between the room temperature and the average water temperature going through those loops. So that would be 87-degree average water temperature would be required to provide 20 BTUs per square foot with a 6-inch tubing spacing and a concrete slab with no floor covering over it. So that sounds pretty good. Now what we wanted to show you too is what happens as you start increasing the tube spacing or you start putting floor covering over it. So let's take that same example now and let's put like an R1 over it. Let's put some carpet and pad or maybe a 3/4 hardwood floor over a radiant slab and see how that changes what we'd have to crank out to that slab to be able to get that same amount of BTU per square foot, that 20 BTU. So follow the line there from the R1, 12-inch on center, the red line, take it down, and now you can see the difference here. Now we're looking at a system where we're going to need to supply about 120, 125 degree water to that zone to be able to get that 20 BTU square foot output. So we're getting close to what a geosource system would be comfortable with, above that 120. I know there are some higher temperature systems coming out now, but that's the number that we're going to keep talking about today, is 120 degrees and lower temperatures. So what would you do to a system like that? Well, certainly tightening it up to a 6-inch on center spacing and still keeping that floor covering would help you a little bit. But that you can use this graph, just use it in conjunction with, if some of you guys have a rad pad that comes from the RPA, it'll show you the resistance value of different type of floor coverings, so you can play with that over here on the numbers, showing you the floor coverings. Or I know a lot of the radiant design programs that you get from Uponor, Watts Radiant, or Vega, or whoever you'd like to use, has this information in there too. So that we're going to show you as choice number one, and probably one of the best choices to match up with a geo system is a concrete slab. Now here's that little radio that I showed you from Yaga a couple slides earlier. And so what they've done cleverly is that they've taken these little muffin fans, I'll call these, like a fan that you'd see in a computer cooling fan or something like that. Very low wattage. All three of these fans can run on about 5 watts of power consumption. They put them on a little circuit board, a little logic here that they can vary the speed of these fans or whisper quiet. But what they've done is they really boost the output of this element by forcing convection through it. Instead of just having natural convection where the cooler air comes in from the bottom, goes through the fins and gets heated up and comes out the top. Now by putting these little fans on there, they can boost the output. In fact, they're claiming about a 250% increase in performance from this emitter with the same temperature water by just forcing the convection through that. Now they've done some other things here that you can see. I don't know what you can see on here, but the fins, they've crimped the fins, they've put them real tight together. They've got big tube or big fin dimension there, the spacing between them. All those things play into the output of a fan coil like that, whether it's a coil on an air conditioner condenser or an emitter for a baseboard. So they've tweaked that, they've engineered that to the as much as they can to get the highest output, and also the thickness of the fins has a difference in the output of it. So if that's something that you're looking at, and this is a good product if you're going to do a retrofit or remodel where they don't have the ability to put in a concrete slab, they still want to go with some kind of hydronic-based system, they would be able to, like to be able to run that with a geo or maybe have a solar component to that, then this would be a good emitter to look at. Now there's other companies that do that. I'm not just trying to spiel a certain brand here. There was kind of an exploded view of what that would look like. You can buy this fin tube right here and put it in a cabinet, or there's different coverings that they offer this in, and then this can be added on later. So you might try a system and say, yeah, it works pretty good. We would like a little bit better performance, or we're going to someday upgrade to a geo system and we want to run that at a lower temperature. Well, then you could go back, and this is available as a retrofit kit. You can see it just snaps right onto the tubes that go through the coil there, and then you put this little controller on it. Very clever system. I expect we're going to see more radiators available with a similar component to it. Another brand, I know a lot of the hydronic guys in here today will recognize the Slant Fin is probably one of the premier fin tube companies out there. They also offer what they call a double stack system. So what they can do on their larger enclosures is you can put 2 elements in it and stack them one on top of the other. Now that, it doesn't quite double the performance of that, but it really does take it up quite a bit. So if you've got the room and the ability to put a little taller enclosure in there, put a double stack of elements in there, and the same thing happens. You'll be able to either get higher outputs or operate that baseboard at a lower temperature and get similar output. Now the other thing that they've done, which was nice, is over the years they used to show these output charts for their fin tube, and I think they used to start either 140 or 150 degrees. Well, they've gone back and they've recalculated those, and now they're taking these output charts all the way down to 110 degrees, which is wise because, again, they realize that the solar market and this geo market, these guys are going to be looking for outputs at much lower temperatures than what they used to publish there. So you can see what happens here on the upper ones. This is just a single element, and they've got different types of element available here. You can see what changes on the element. Of course, is the dimension of the element, the thickness of the fin. They tweak some things on the element to get a little higher output. But this bottom column here shows you with the 2-tiered model. So you can see what happens. You don't quite double the output, but you can see you get quite a bit better output. They're talking all the way up to at 120 degrees. Let's keep using that 120 degree number with a double tier. I mean, here we are up in the 500 BTUs per linear foot of output from that double stack baseboard. So that's something to look at too if you want to use a product that's readily available. Yet another product that I found when I was kind of searching around to see what's out there is this product from Smiths. And what they've done is they've basically taken that same concept of a double-tiered or double-stacked element, and they put it into one product. So Here they've got both tubes going through that fin as a one-piece fin. You can see they've got them real tight together. They've got a very deep fin. It's a very tall fin, 3/4 copper going through that. What's neat about this product, it can be fed a couple different ways. You could feed both those together, or you could go down one with the supply and return back through the other, and it does change the output depending on how you choose to configure the piping on that. But it's a nice-looking element. It's got a nice enclosure to it, so check into that. They do show some outputs at very low temperatures. I think their temperatures are going down about 100-degree average supply temperature with their output charts. Now, a good way to do a distribution system, if you're going to go with a panel radiator, a fin tube, or one of those other type of emitters, is what we like to call a home run system or a manifold distribution system. You wouldn't want to put these in series, because if you're feeding the low temperature water here, by the time it goes through this radiator and it gets to this radiator and this one all the way back to the end radiator, you're going to be down to such a low water temperature you're not going to get any output. So you want to either parallel these or put them on a system like this where they're going to have a home run, so every radiator is supplied with the exact same temperature from this manifold. A couple different ways you could zone a system like this. Thermostatic radiator valve, which Caleffi is going to introduce. Watch for those early next year. We're going to have a line of thermostatic radiator valves available, so they could be zoned right at each individual radiator. So every room or every panel radiator in every room could have its own temperature control, which would be nice. That would give the occupants kind of an ideal way to regulate the temperature if they want to keep some bedrooms cooler than others, or turn some off when they're empty or something like that. Now, this could also be zoned back at our manifold here. We've got actuators that go on our manifold, so if you chose to put a thermostat in this room, a wall thermostat, and then take it back to the 24-volt actuator here, that's another option. So this is a very nice system because it allows you to pipe out to those radiators. Sometimes the tubing is small as 3/8 diameter PEX or PEX tubing, so it allows you to snake that through a building for a retrofit or remodel project. So this, I think, you're going to see as a more common retrofit product because of the ability to get it into a building without having to tear open a lot of walls or get in there and run ductwork or bigger piping and stuff. So now, when we talk about heat pumps, so everything that we're talking about today is probably pretty much on the right-hand side of the drawings here. So here's a system where we've got a reversible water-to-water heat pump. It could be in the heating mode, or it has a reversing valve, so it can be a heating or cooling mode. And it shows it going over to a buffer tank. Now that's important. If your load and your source side don't exactly match, it's a good idea to have a buffer tank so that this pump isn't short cycling every time it kicks on and off. So we make a tank available for that in a bunch of different sizes that makes it really easy to do this. One of the things that the Geo people have been screaming for years is say, give us some tanks with some big port connections and well insulated, so if we're going to run this as a chilled water application, we don't have to worry about sweating and stuff on the tank. So we recently addressed that market. We came out with a tank that would work either in the heating application that you've seen there, or the same thing applies to a chilled water application. If you want to have a little bit of buffer storage here, you're going to have a tank certainly that's rated for that application, being that it's insulated completely around so it doesn't sweat and drip on your floor, and also give you the capacity to buffer these multiple zones here. To start zoning the system with different size air handlers or multiple zones, it's very important that you have a buffer tank to be able to have parking space so you're not cycling that heat pump so much. And so this is what we came up with to address that market, is what we call our ThermoCon tank. And we're giving you a tank available in the 58 or 119-gallon version. And what we've done is we put in 7 2-inch ports on different sides of the tank. So you have 2 directly across from one another, 180, and then at 90 degrees from that, we've got 3 additional 2-inch ports. So you've got 7 ports. So now that makes it really easy to put a heat pump right into this side and then take your load off the opposite side here. It also serves as a little bit of a hydro separator. I mean, it really is a supersized hydro separator, and by giving it a dome top like that, you can put an air vent in that center port there and get some pretty good air removal from this. So it's foam insulated all around, so you don't have to worry about it sweating and dripping on your floor there. So we'll give you some ports at the top that you can put sensors in. We give you the center port here because that's an ideal place to put the sensor that would operate your heat pump. If you're reading the temperature at the center of this tank, that's the control that would turn the heat pump on. So the heat pump is really looking at this as its load now, not as the distribution side, the radiators or the panel radiators or the radiant tubing. It's looking at this as its load, so that's controlling thermostat would go into a port in this tank, and that's what turns it on. The tank gets up to either in the heating season the hot temperature, cooling season to the cooled water temperature, then it shuts off the system, and then you just basically sip off the load on this side of it as needed. Another thing that's becoming really popular, and it works really nicely with these zone systems like that, whether you're using the actuators or the thermostatic radiator valves of these delta P pumps. So now that gives the pump the ability to modulate based on how many zones are opening and closing. So again, it just increases the efficiency of the system. They use quite a bit less power, and being able to modulate down at lower speed when only 1 or 2 zones are calling saves you some additional power consumption. Because really in the end, I mean, we're looking to save energy both in the electrical distribution side of it, what it takes to run the pumps and the controls, as well as the heat emitters with the heat pump or the solar component. Now, if you do have a system where you've got a matched load, which doesn't happen very often, but it is possible to pipe a system like we're showing here. So we're going to go through these drawings now. We're going to start with a very simple one, and they're going to get more complicated as we go. We're going to start bringing in boilers. We're going to start bringing in solar. We're going to start bringing in additional buffer tanks. But this is probably the most simple one that you would probably come across. And basically, the heat pump here is going directly to a single load. Notice that these aren't zones, so you're not going to have the ability of just one zone call on. Let's say you've got a 15,000 BTU load here, you've got a 3-ton heat pump here, well, you're going to have some serious short cycling. So this, as long as this load and source side match up, this would work fine. But again, most people, if you're looking at buildings, are going to want some kind of zoning or some way to pull on different loads at different times. So this would have a fairly limited application, but it is possible. One thing I want to point out, I know we're not talking about the source side, but this is really critical if you're going to pipe a system like this. This pump here, notice what it's doing. It's pumping through the heat pump as well as through all the piping and through the loop. So it's critical that that gets sized properly. Don't size that just for your loops or just size it for the heat pump, because you've got this whole load to consider there. I think we talked about that a little bit when we talked about the source side, but I just want you to remember that when you look at these drawings and say, oh yeah, I'm just going to throw in a little pump here and then a delta P pump here, and away you go. You do have to know what's going on as far as the sizing of that pump there. All right, so let's take and throw one component in between there, and let's call that the ThermoCon tank. So now you can see what's going on over here on the distribution side. Now we've got some zoning going on. So we've got some zoning going on here with some electric zone valves and some zoning on the manifold. So now it's important that we have some kind of buffer tank. So if one of these zones is calling on maybe a mild day or something like that, we're not going to be cycling our heat pump on and off. We do give you a chart in the back of Hydronics number 9 in Appendix C. It does tell you how to size this buffer tank, so if you know what these loads are, it'll tell you what capacity tank you would need to keep this from short cycling. So you determine what you want for an on-off cycle on this heat pump, and then you can size this tank accordingly. Now we're starting to throw in some other components here. You can see we're throwing a Discal air eliminator on this side. We've got a check valve in there. Again, we've got a variable speed delta P pump. Some of our zone valves there, that could be our Z1 valve if you're going to zone at the boiler room here, or if you're going to use the manifold, we can zone it at the actuators, or like I showed you earlier, we'll have the thermostatic radiators valve available soon. One of our boiler trim packages here could be used on this side, even though it was called a boiler trim package, it could be used on a geo system. It gives you the expansion tank and the fill valve and the connection check valve here, fill valve, backflow preventer if you want. It just makes it real simple for you to get to all that in one box and put it in there. So let's see, what else did I want to talk about on here? I think that's going to, oh, okay, this is what's happening on this one. So now we're controlling the heat pump by an outdoor reset control. Again, we weren't going to talk about the source side today, but just so you know what's going on here, that's where we're using that center well on that ThermoCon tank to put the sensor that's now driving this outdoor reset control, and that's what's in charge of how the heat pump comes on and off. Now you can make these as simple or as complex as you want on your control side of it. We won't talk a lot about the control possibilities or options out there today. We want to talk more about the piping side of it. Now another component that you'll find in a lot of heat pumps is what's called a desuperheater. And basically what the desuperheater is, it's kind of an oil to water flat plate heat exchanger typically. So what it's going to do is going to take some of the hot gas from the compressor here, and it's going to flow the water from a domestic water tank through there. So you're going to recover some of that energy from the compressor when it's running and put it right into the domestic water tank. Well, it just so happens that the ThermoCon tank is ideal for that application too, because it is an enamel-lined tank, so you can't put domestic water in it. And by having all these ports, look what we've done here. So now we're pulling some energy off that desuperheater. We've got a little bronze stainless steel circulator. Sometimes those are built right into the heat pump. That circulates it through the B side or the water side of that plate heat exchanger, now heats up this tank. Now there's going to be times when you don't get enough or any of the energy from that desuperheater if this isn't running or isn't running long enough to cover your domestic water load. Well, you'd want a backup element there. And by using this tank with those additional ports, you can buy this Chromalox element that would screw right into. There's other manufacturers that they make elements that have the control and the reset and their UL listed. Screw that right into one of the ports. If you want to just heat the upper part of that tank, if that's enough hot water, you can screw it in an upper port and keep the top half of that tank heated with resistance heat. Or if you need a little more capacity, this could screw into this middle port here. Now you've got half the capacity of the tank as a backup. The other thing that's important on this drawing, we talked about this in solar, and I know we harp on this quite a bit, but you need to use a thermostatic mixing valve on the output of these water heaters because you've got the potential this time to get pretty hot if you're going to have a, certainly with a solar input, or if this isn't regulated to a certain temperature, you don't want to be scalding people or sending out too hot water. So we're showing that with a thermostatic mixing valve. Ideally, that would be a Caleffi valve, of course. All right, let's get a little bit more complicated here. How am I doing for time? Looking pretty good. So we've thrown in a couple more components here on the source side. We put a hydro separator in here so this pump can behave with these pumps here. But now what we've done here over on the distribution side is we've put a couple heat pumps. Now these could be staged in. You know, one heat pump when the load is low, the second one could kick in, the third one can kick in as needed. And also you can sequence these and exercise them. So you could go around, so maybe the first time this one kicks, the next day this one kick on. So that way you're going to exercise and load them up all evenly so one's not doing all the work there. And now what we've done here is we've shown you this here with the hydro separator. We've got let's call this a single pump system. So we're taking a single pump and then we're bringing these heat pumps on with zone valves here, electric zone valves. So if one is calling, this zone valve opens and it gives it the heat. In this case, we're showing it in the heating mode. You can see the red tank over here indicates we're in the heating mode. And then as more heat's required, they would step in like that. We're also showing one of our flow cals here, so we know that every one of these is get the exact amount of GPM flow rate that it needs. We'll put a flow cal there on that line to the heat pump, and of course little isolation valves and some purge valves and stuff here. But another nice way to do this is again with a variable speed pressure regulated circulator. So if only one of these heat pumps is calling on, then that pump would run at a speed to give that the amount of flow that it needs. As the second and third one comes on, this thing starts to rev up. So that's a nice matchup with the zone valve system like that, is to use a delta P pump and let it modulate across its range based on the load that's being presented to it. And then the same thing we're doing here on the other side of the heat pump. Now we've got the zone valves on this so that we can zone that into the buffer tank here. Same thing, a variable speed regulator, because they work so nicely with these flow cal valves, and with the zone systems like that, as the zones kick on and off, the flow cal is going to ensure that we get the right amount of flow through each and every one of these, regardless of what variation of heat pumps are kicking on. And then the same thing on the distribution side over here from the ThermoCon tank. We've got a Discal air purger there. We're doubling up on the air purgers here. Typically, this is enough air purger, having this one on the dome, the high point of that tank. Sometimes if you've got a system that has a lot of ups and downs or a lot of small diameter tubing, it's nice to put another air elimination device like a Discal in there, because that'll assure that this pump is never going to have air bubbles or have the potential to cavitate on you. Same thing over here. This could be zoned with our Z1 valves, or could have valves out at the heat emitters themselves. So a little bit more complexity in that system, but very doable, a very common system out there. We talked about the tank. There's another picture of it just showing you the different sizes that's available, and it is a porcelain lined. Now, when you use it in a domestic water application, we've given you a bunch of 3/4 tappings on the top, so you can add anode rods into that earlier picture where I showed it connected to the desuperheater. Well, that would be a tank holding domestic water, then potable water, so you'd want to drop some anode rods in it there. All right, now on this one here, we've taken the buffer tank out, and now we're putting 2 hydro separators on. So we've got a hydro separator over here on the source side. We've got a hydro separator on the load side. Again, we're counting on these heat pumps being able to modulate or step in and out pretty close to what the load is here. So again, variable speed delta P pumps on here. So the pumps will change their speed based on how many heat pumps are kicking on and also how much load is kicking on. So it's possible to do a system like that if you got your systems matched pretty closely. Now we are seeing heat pumps now that have variable outputs, variable speed compressors and stuff like that. So that makes a system like this a little bit more, what's a good word, doable, I guess, with just a hydro separator instead of a buffer tank. Same thing here. We're using a single pump system. We've got zone valves on our on both sides of the heat pumps here, both coming from the source side into the heat pumps and going out on our load side. We've got it zoned with valves. All right, now here's a system that's going to do heating and cooling. Up until now, we've been talking pretty much about heating applications, but let's say you've got a job. Maybe this is in an area like in Colorado or something where they've got a month or two in the summer where they need a little bit of cooling application. So what we've done in this one here, now we've got the heat pump, same desuperheater here to make a little bit of domestic hot water in the tank up here, backup element as we talked about. Now we've got a buffer tank on our heating load side. And that's in there because, again, we've got a multi-zone, maybe a micro-zone system here that we want to have a little bit of parking space or a little bit of buffer to smooth out the operation of the heat pump here. So when that's running, it's going directly from in the heating mode, it's going from the heat pump into the buffer tank, being stored there and then sipping off as it needs for the heating zones here. But now what we've got here is we've got a single air handler, air conditioner that's sized pretty close or exactly to what this heat pump is. So that doesn't really need a buffer tank on the chilled water side. So you can see what we've done here is we've put in one of our three-way diverting Z1 valves in there that can divert when it's in the heating mode, the heat pump, it's going to go into the buffer tank. When it's in the cooling mode, we're bypassing the buffer tank and we're going to go directly from the heat pump to the air conditioning to the cooling load on it. So that's a simple system. But again, the limitations are there that this heat pump and that emitter for the cooling side match up pretty closely so you're not short cycling there. So I think we see systems like that, like I said, in cooler climates where there's not much, if any, big loads on the cooling side of it. Now here's a system in a cooling only mode. So now what's happened is you can see the tanks turn from red to blue. So that would, I mean, what we're doing here is we've got multiple air handlers, multiple loads on the cooling side. So now we've chosen to put the buffer tank back in there to buffer the cooling side of this. So same thing here. We've got a variable speed pump that we're showing on pretty much all these drawings. The price of those has really come down. All the manufacturers I know, the big price decrease at the end of last year, so it's making that a more viable product for you guys to use in geo applications, hydronic applications, solar applications even. We're seeing these variable speed, high efficiency pumps being more and more common. A couple things I've thrown in here. We've thrown some vents at the high point. If this is a multi-story building, it's not a bad idea to have some flow-type air vents at the highest point in the system, so any air that did migrate up there when the system was off, for example, when the pump does shut off and all the loads are met, pump shuts off, you do have the potential for any air bubbles that didn't get scrubbed out of the system here to rise up here, so that's a good place to have a couple air vents. You'll notice those on our manifolds also, too. So if you had a manifold distribution system here, by default, you would get two of these little air vents on the manifold, both on the supply and return, to assure that you don't get any problems with airlocks up at the top there. So here, what we've done here is you can see we've grayed out the heating side of it now. So when we're in the cooling only mode, this is what's happening with that tank. You'll see on the next slide, we're going to switch off of the cooling mode and turn this into a hot water buffer tank. So there we are. The cooling load has gone away, but we do have a heating load. Now, there is a limitation to the system, and there was a bunch of these put in not far from where I live here in Arkansas years ago, where they have some retirement homes down there, and they put the single, what we call two-pipe system in, and they have to choose a date in the spring and the fall where they switch over from heating to cooling because they can't run both at the same time. They've got little air handlers, and they're either heating and cooling. Well, they learned pretty early on that there was a problem with that. Is some of the rooms that are on the south side of the building, they get a lot of passive solar gain, and they're saying, gosh, we still need our cooling. You know, you turn this thing off every year in September, and we're sweating in here. And the people on the other side, well, I get up in the morning, and I'm cold. I need to turn the heat on. So that would be a limitation of a system like that. It wouldn't be easier possible to switch quickly from heating to cooling, because now you've got your buffer tank loaded up, in this case with heating. Now let's say the sun comes up by noon, people are saying, I'm getting too hot in here, I need my cooling back on. Well, it's not going to be possible to switch gears quickly there. So this would be a fairly limited application system once again, but there are applications where this system does fit. So you can see what we're doing here is we're just showing you a lot of different conceptual drawings on different ways you can do that to get you thinking outside of the box of a system that maybe you've done for years, always the same way, a rubber stamp system. We just want to show you with today's components and technology that there's a lot of different ways that you can do these systems from mild to wild, let's say. All right, let's take it a little bit further, another step further. So now, again, we still have multiple heat pumps in here, and we've got what's called a four-pipe system. So now we've got the ability to store hot and cold water, chilled water and heating water at the same time. So we've added two buffer tanks to this system. This is going to get a little bit more trickier here. What we've done here is we've put three-way diverting valves in here so you can divert, depending on what mode this is in, whether it's in the heating or cooling mode. Now it's going to divert the flow to the appropriate tank and the appropriate load here. So if this heat pump or these heat pumps happen to be in the cooling mode, supplying chilled water, then this valve is going to toggle over. So the flow comes in here, it's going to toggle over. You can see it's going to go into the chilled water tank. The blue lines, obviously, are the cold water. The red, of course, are the heating loads. So that's what's changing on this is now we put in the second tank. Now we've got the ability to store some energy for both the heating and cooling loads, and we're doing that by toggling this three-way valve here. We've put some check valves in there so we don't get backflow, because you're going to have to choose with this one. Again, you're choosing between one or the other. You can't feed both of these lines simultaneously, so we want to make sure we've got some check protection there so we're not going to backfeed from the hot and cold there. What else have we put in here? Just some good commonsensical piping application tips there, about getting your pipe size, so you make sure you've got that 2 feet per second to make sure you get good air removal out of that piping. I know some of these are probably getting a little tricky for you guys to read as I get more and more stuff in the drawings. The print and the size of everything gets smaller, but again, these are all in the Hydronics 9 issues, so pull them out when you get a chance. What else have we thrown in here that we haven't seen before? Here's a little fluid feeder that we put on this side to make sure if any air perps out of the loop field here that we've got a little feeder to maintain that. Circulators, I think that's pretty much what's changed in that. Now with this 4-pipe system, you can see we've got air vents on all the supply and return on both the heating and cooling piping in the building. Now this is actually the system, that building I talked about down there in Arkansas. They actually did go back and retrofit that entire, in fact there's a bunch of buildings down there in Mountain Home, Arkansas, with 4-pipe systems, because they realized there was just no way that they were going to be able to keep everybody happy in those homes down there by having just either heating or cooling. All right, moving along. What have we done here? So now we've taken this system. Let's see. Oh, the zone valves here. You can see we've got an additional zone valve here. So now we've got our diverting zone valve as well as another zone valve on the other side there for protection. So really the same drawing as the one previously, with just zone valves on the heat pumps now. Zone valves on both sides here. This has a single pump system. Again, the same caution would apply here, that this pump now has to be sized to handle the load of all 3 of these heat pumps through this piping here. And of course, this piping would need to be sized to handle the load of all those also. So now we're bringing those on with zone valves instead of individual pumps. What else did we bring into this? Pretty much the same thing here. We're showing you variable speed delta P pumps on both the heating and cooling side of this, because you can see we've got these systems both multi-zoned for the heating and cooling loads. This side we put a disc L on the input side to this tank. On this one here, since it's hot water, we put that on the output side, because you want to get your air removed at the highest temperature in the system. Certainly in the heating system, that's going to be the hottest temperature point there. On this system here, you've got cold water coming in here, warmer water going there. That's going to be a little bit better spot to remove the air on that. So that's, I think, some of the changes as we go through these drawings here. All right, now here's kind of a clever application. This one I'm going to have to go to my notes on, because this one I just started reading up on this a little bit more today. So what we've got the ability to do with this drawing here is we've got the heat pumps up there on the upper left-hand side that would switch from heating or cooling. You can see usually when we've got them written in red here, they're in the heating mode. Now that's got a reversing valve that could go in the cooling mode. But now if both of these were running for heating cooling applications, we could put another heat pump in there and really get some real high COP. We get the COP on this thing up around 7, because now we put a heat pump in here that would supply heating and cooling at the same time, what we'll call a simultaneous load heat pump. So what that does, it increases the efficiency of that heat pump by having both loads on at the same time. Now, again, a little limitation on that is both those heat pumps above would have to be in the heating and cooling for that to be able to work right. So basically, and I'm going to read this right out of Hydronics 9 because it is a little bit complicated. So the COP of the simultaneous load heat pump would be the ratio of the total desirable heat transfer effect divided by the total electrical input. So in other words, if that heat pump down there in the center is on a 30 amp breaker, that would be the electrical input. We give you a formula for calculating that COP when you put it in a simultaneous system like that. And then the example in Hydronics 9 when you get is we've got that in there, and we're showing with both of those COP being 4 for those 2 heat pumps. By putting that third one in there at the bottom run simultaneously, you do the math on that and you get that up to a 7.0 COP. So that means that your heat pump is really creating 7 times the amount of energy that's put into it. The electrical energy that's going into it is coming out of that. So that's a really unique way to leverage that application. Of course, a little bit more piping, a little bit more complication, and a little bit more cost involved in that. But just something to get you thinking about there. All right, heating and cooling, what else on this? I think that's pretty much the same thing. You know, one thing that we're trying to bring to the geo industry is the concept of expansion and air elimination device. I know a lot of the geo guys that are plumbing out there now don't bother putting in the air elimination devices, either a central air elimination device, or you can see a little air elimination on the hydro separators that we've shown in this different drawings, and expansion tanks. Because what happens when you cool water is the volume contracts just like when you heat water, it expands. So you really need a little bit of reservoir, a little bit of capacity there to handle the changing in temperature in this fluid here, because it does change, between heating and cooling and different load conditions. So we're showing it with an expansion tank, and also a little fill system here. If this is a glycol or a methanol or whatever transfer fluid you're using in this here, you can put a little feeder in, because if you start putting air vents on a system and they do burp a little bit of air out of there, now you've got the potential to cavitate that pump. So in this case, that being a heat transfer fluid, not just plain water, we would want to put that in through some kind of feeder or fill system. On this side over here, since this is just a domestic water, potable water in this, now we're feeding that with a regular expansion tank, and just one of our autofill valves could be used on that side. So just something to think about when you start introducing hydronic components in the geo systems that, think like a hydronic system as far as the components you're going to add. Another thing I don't know that we've talked about here, you could have the center ports of these tanks, again, would be your sensor wells. So whatever sensor, whatever control is driving the system, you've got the ability to put that sensor in a good spot in those tanks by using those center ports. All it would take would be like a 2 by 3/4 reducing bushing, and then the dry well could screw right into that. Let's see what else on this drawing. I think I've pretty much caught all the components there. All right, now there might be an application where you've got a geosystem that's going to need a little help sometimes. Maybe this heat pump wasn't sized to handle the load under severe conditions, or it was purposely sized that there would be a boiler supplement or addition to it. So here we're showing just taking a little ModCon boiler, maybe a Lochinvar Knight or whatever you'd like for a brand there, would be tied into the system. So now what we're doing with this here is we're tying it in a way that it's got the ability to make domestic hot water with an indirect tank. So there's the ModCon boiler with a little 3-way diverting valve that it can cover the domestic water load, and we still have the ability to put some heat in that with a desuperheater also from the heat pump. So now that could go directly into the potable water of the tank from the desuperheater, and then we've got the ability to heat that tank with the boiler if the heat pump doesn't happen to be running. And we also have a buffer tank here. So now we've got the geo coming in here, the ability of that to go into the buffer tank. We've got the ModCon that can go directly to the domestic water load. And then we've got our distribution side. In this case, we're showing some panel radiators, thermostatic valves that we talked about earlier, variable speed pressure delta heat pump on that, air elimination here. And then that would be run, or could be run, on an outdoor reset control. So now this would tell this or the boiler what temperature to supply to the system based on outdoor reset. So we just put a little bit more control logic to it, as well as some more components in the boiler here, as well as an indirect tank. Let's see, make sure I got everything on this. Yeah, I think the same thing there. There's our boiler trim package there and some air vents, disco air remover there. And that's just, again, a 3-way Z1 valve there. You can see what happens here is the flow goes into the center port and the T in the bottom always, and it either goes to the B port or to the A port. So it's either going to go to the tank or it's going to go directly into the heating load, or the heating buffer tank, I should say. I think that's pretty much it on that drawing. Now solar. Now this is going to be more and more common, because now here's bringing 2 green energies together in a really unique package. So now what we're going to do is we're going to put on some solar panels on the roof and be able to put that into the system also. So now this gets to be a little bit more piping. You can see everything starts to get smaller as we jam more stuff into the picture. So now we've got some solar collectors on the roof, a little solar pump station there. This would be a closed loop glycol system. So now this has to be separated from the water that's obviously in your domestic water tank and also in your heating system here. So what we're doing is we're bringing our solar in through one of our solar pump stations here, and we're bringing that into the coils into our solar tank here. Again, you can see a three-way diverting valve there, so we've got the ability now for the solar to come on in the morning, cover your domestic hot water load first in that solar tank, in the SolarCon tank, and then it can toggle over, and in this case, we're putting it into the loop field. So if you've got a job where you want to start maybe in the fall months, you want to start charging up your loop field, put some temperature down into the ground there to help with your heat pump when the heating season rolls around. That's what we're doing with any excess heat from the solar. We can put it into the loop field. Now this here also shows a backup element in the solar tank there. So now you've got the ability, you can run this with solar or you can run with electric element. And again, this could have a desuperheater on it here. I think we showed that. There's a desuperheater. I know you can't read that anymore. There's a desuperheater that can add energy to the domestic water side of the tank. The solar can add the energy to the tank via the indirect coils. And you've got the ability, maybe you've got some low off-peak rates for electricity. You kick that element on and also heat up that tank. Then over here, we're doing pretty much the same thing, taking the energy from the heat pump, storing it in the ThermoCon tank here. We're showing this in the heating mode now. You can see again we've grayed out the cooling side of this here. So now this tank is red. Going to the heating mode, again a manifold distribution system here going out to your radiant or panel radiators, whatever that might be. Multi-zone, so it's important again that we have a way to regulate the flow to that. We've shown in all these here a pressure-regulated delta P pump. We think that's the way the industry's going. Certainly if you choose to use a regular fixed-speed pump, you would want to put a pressure-activated bypass on the end of these manifolds somewhere in the piping system so that as zones start shutting off, you would just shed some of that pump head through the bypass valve instead of using the pump that can automatically do that by reducing its output by changing its speed. If I mentioned that early on or not, but what else on this drawing? I think I've covered everything on that. Now, I did see a system like that recently last week when I was up in Fairbanks at Weller School. That's exactly what they've done up there is they put in a system. I think they've got about 8 collectors on the side of the building, and they're just using that to dump into the loop field. In fact, they're not even, for some reason, doing a domestic water load. And what they're doing is they're going to run it this year without the solar input and get some baseline information to see how that system performs on just the heat pump for the school. And then they'll bring on the solar next year to see how much they're actually, so that data log that system, and they'll be able to tell how much the solar is actually going to do to it. They did find an excellent site up there to do that, because of the ground temperatures and stuff like that up there in the permafrost. They found a site up on a hill there in Fairbanks where they don't have to worry about groundwater and stuff stealing away some of that energy that they're going to dump down to the loop field until they need it. So another application to think about is tying the solar in it. So now we've showed you systems that we bring the solar in it. We can bring a boiler for a backup. You've got the electric elements for a backup. Different ways of doing the distribution side with a storage tank, with the ThermoCon tank, with the hydro separator. We're showing the heating, cooling. I visited a job up there with Nathan and Soldotna up on the Kenai when I was up there, and he put a system in that had some radiant ceiling panels, which were kind of unique. So he had a ThermoCon tank in there. It was not a geo system, it was a boiler system, but he was doing some spot heating with they're kind of like an aluminum panel that drops right into the ceiling grid, which is nice. And that's another application, we didn't talk about that earlier, maybe that you can do a ceiling or wall heating system that would run at a low temperature. But those aluminum panels make it really unique application, especially on a commercial building. What he did is he put them right over all the desks of the girls in the office up there. So they say, oh, I'm a little cold, where they typically plug in a little electric heater under their desk or something. Now he's put all those little overhead panel heaters on his own on thermostat that the gals or the guys in the office get cold. They can just kick on the thermostat and they can bring on that little spot heater right over the top of them without kicking on the whole radiant system. I thought that was a very clever application for that. So that pretty much takes us through the drawings here. We had a couple others in here that I want to show you. This is another way that you could cover loading into a tank here, but using the coils instead of using the tank capacity. And we happen to have a solar tank that does have large diameter coils. Our coils are 1.5 inch diameter. We've got, I think, 36 feet of coil on the bottom, 30 feet at the top. They could be combined together here, so you can have 66 feet of coil going from the bottom to all the way to the very top of the tank. Large diameter, so you'd be able to take the output of this heat pump here and pipe it into this tank via the coils here instead of going into the water. And now you can pull off either your domestic load, or this could be a heating load coming off the capacity, the water that's in the tank instead of the coil. So that's just another way that you could use a tank if you have a tank that has the ability to take that kind of flow rate. What else on that? I think everything else we've talked about on that. Again, a little boiler trim package, expansion tank on the side here, temperature control. So that's what's driving this system here is the temperature control, reading the temperature of the tank. Again, the geo heat pump is looking at the tank as its target that it's shooting to maintained by the sensor mounted in the center port of that tank. Got it? All right. Pretty close here to the time. So this is what we've got for webinars coming up yet this year. So we did Hydronics 3 today. Dan Foley's a good friend of mine. He's a mechanical contractor back in Virginia. He's offered to be our guest speaker on our next webinar. And we've asked him to talk about, he's got a lot of experience with the old systems back there, a lot of experience with retrofits. He's doing a lot with geo conversions back there. So I thought he would be a good person to speak on some of the problems and some of the startup issues that he sees in the fall and what kind of components he's using to solve those with some of the systems, especially when they start converting old cast iron radiator systems. So he's going to be our guest host on the next webinar. Then October 27th, we're going to do another solar thermal on, we get a lot of calls, a lot of questions about drain back systems. So we're going to do a webinar just on solar drain back systems. We're going to show you some unique ways to use collectors and tanks and different ways to integrate the drain back systems with a heating system and stuff like that. So keep an eye out for that one. Now the other thing that we're looking at doing, and we want some input from you folks on this, is we're thinking about next year's webinar series, and we've got one left that we want to do one more in November. We usually take December off on the webinar circuit here, but what we're thinking about doing, and I put a slide in here that reminds me of this, is doing kind of a show and tell. We don't know exactly what we're going to call it, but what I want to do is we're going to get a webcam set up. GoToWebinar just has a new function they put on as a webinar feature. We haven't tried it yet. We will make sure that works. But what I want to do is take various components that Caleffi builds and actually take them apart on the camera and show you what goes on, how they work, what's different and unique about the Caleffi thing, but also what to look for when you have a component that you don't think is working right. And a classic example of that is we get a lot of backflow preventers that, contractors call and say, it drifts, it's leaking, there's something wrong with it, I'm sending it back, I want a new one, blah, blah, blah. Well, 99% of the time we get those back and we take them apart and there's nothing wrong with them. So we thought if we do a little hands-on demo in front of a webcam and actually take that valve, take it apart right in front of the camera and show you how it works, what's going on in there, and where all these leaks could develop inside there. And I think that's going to give people a better understanding. So we'll do that on different components. We'll do that probably with our solar controllers, probably take apart some air and dirt elimination devices, maybe even cut away some of our hydro separators so you can kind of, I know some people learn better by seeing things that way as opposed to just talking about them. And what got me thinking about that, we used to, I know my son Max is tuned in today, we used to read these to him when he was little. It was the Magic School Bus series. If you have a youngster, a grandchild, or a niece or a nephew, this is a great book to read. And what Mrs. Frizzle was the teacher in these, she would take the kids on a school bus and they would go through all these different projects. And they would take this bus and they'd have this one here. They went to the water works and she explained what, how pressure works, how flow works, with, flow rates and stuff like that. They would go into the center of the earth and stuff. And that's what got me thinking about the show and tell thing, because it was I think it was good for me too. I enjoyed them, I think, as much as Max did, just seeing how, take a drive inside of a component or inside of a system or inside the, circulation system of your body or something like that and see how things work. So that was our motivation for what we're going to be doing next on some of our webinars. I think we still want to bring some guest hosts. So if there's somebody out there that would like to join us and host a webinar, if they have a topic they think is that everybody should know about, certainly drop us a line. We'd like to consider that with you and put you on with it. So with that in mind, I'm going to leave the last couple minutes and see if there's any questions on anything we talked about today or any of the series. I know this has been a lot of information over the past 3 webinars on the series. There is a lot to talk about. This is 66 pages of information in Hydronics 9, so it's a fairly a deep subject, but I'd be glad to try and answer any questions while we're still on the air. If Mark or somebody back there in the office wants to read some off, we'll get to them. If not, send them in. If you want a question and answer, just send me an email. Yeah, Mark, I can hear you.
Yeah, we have a few questions and a few minutes left here. You spoke about the desuperheaters. The question, does heating hot water or preheating hot water using the desuperheater, does that reduce the space heating or cooling output of the heat pump system?
Well, it is taken. The way it works is it works on the hot gas side of it. So yeah, any energy that you're going to steal off the compressor on that side of it, you're taking away from the heating capacity of that heat pump there. Now I know some of the heat pumps have controls that can turn that off at a certain point. You know, they can stage that in and out. But yeah, I mean, there is no free energy. It's coming from somewhere. There was something that I wanted to read about that. I might have skipped over that. If I can find it quickly, I'll read that. On those desuperheaters in Hydronics 9, I've got so many notes here that it might take me a minute to pull that out.
I think the question was, if an investment in a geothermal heat system is going to be made on a facility, is it a no-brainer to also do preheating of hot water?
Yeah, I would think so. You know, it's a simple component. I don't know. I would guess. Again, I'm not very up to speed on the actual heat pump itself. That's not something we make or offer. I've got to learn more about that myself. But I would think that's either available or as an option, or it probably comes in quite a few of the geo pumps that are offered out there.
Okay.
And what's something about that? I keep looking as you ask me more questions, because there was something that kind of jogged for me.
Along the issues of heat pump short cycling and using a buffer tank,
yep.
There's reference to a formula for sizing that tank to get a certain frequency of on-off cycles. Is there, however, some type of rule of thumb as far as your smallest zone heat demand versus the heat output capacity?
I know that geo manufacturers will have a rule of thumb that they say how many gallons of buffer tank capacity they'd like to see based on the output of their, whether it's a 3-ton or a 4-ton or a 5-ton heat pump. They do give you some recommendations, some guidelines for the size of buffer tank they would like to see to that, and that information is also available in the IXPA design manual. I know they've got some rules and thumbs. I mean, we at Caleffi don't necessarily have that. That's something you'd want to get from your manufacturer, because again, you want to make sure that you're covering, protecting their equipment and the warranty on that by not short cycling it.
Okay. All right. Another question is, I think you addressed it in one of your latter slides. It was, and there seems to be a lot of interest in combining renewable energies on a system, solar as an example with geo. And
right.
Before the slide, there was a question concerning tying a solar thermal system into a geo system. And the question was along the lines of, is the heat produced from the solar side of the system better put to use by preheating hot water versus putting into the ground loops for systems that have a long heating season? And I think your schematic basically, I think, answered that, if I'm correct. Is that
well, yeah, and you got to look at the loads. I mean, without knowing what the domestic hot water load would be in that building. I mean, if it happens to be a commercial building and there's a big domestic hot water load, I mean, you want to give the solar the best opportunity to cover a load. So the lowest temperature load is going to be the best load. If that happens to be the domestic water, just getting it up to, say, 122 degrees, and it's a large domestic water load, again, for a hotel or a bigger job, that might be the better load to cover first. If it's a small domestic hot water load, they only need 40 or 50 gallons for a small residence or something like that. Cover that load and then start dumping it in the field. So you got to, what the biggest unknown, I think, with starting to dump solar into these loop fields is, can the heat stay in there until you need it? Is it going to get washed away? It's going to be that's going to be a hard thing to determine until we get some of these systems going and start data logging how much of that energy that you drove into there from the solar is actually going to stay in there and be able to be pulled back out and used. So if a bunch of it's slipping away, you might be able to use it for a better use first, which would be your domestic hot water, and then whatever's left, since your solar's running, there's no more load on it, we're going to the loop field. But yeah, I mean, you always want to use your energy in the smartest locations first, and then step it down from there to the, pick the best load first and then just start moving down the line.
By the way, we got a clarification on that earlier question on the desuperheater from a Paul. During the cooling mode, the desuperheater heat is free.
Yeah, right.
I suppose, rather than sending the heat down into the ground loop, you're basically using it for hot water.
Yeah, that's exactly right. Yeah, that's what I was trying to come up with here as I was looking through these pages. That's exactly right, because why load up your loop field to a warmer temperature when you can pull that temperature off, as long as there's a domestic water load there. Again, what I'm finding down, I got the desuperheater on my mother-in-law's thing, and it's, she lives down there by herself. She's got a 30-gallon water heater, so that load gets covered and goes away pretty quickly, and then it goes back out. It happens to be a pond loop instead of a well system, but you're exactly right in the cooling mode.
There was several questions concerning some slides you had with the application of a hydraulic separator, both on the source side as well as the load side. I think those are probably better answered because I think the question answer is going to be long. But there are some questions concerning dirt. We talked a lot about air.
Mm-hmm.
What is your suggestion concerning the handling of dirt on your load side?
Well, yeah, I mean, like any system, you don't want to have dirt in it. It's a brand new system. It seems like brand new systems, it's a little easier to get a handle on that. If you flush them good with a good, powerful pump when you purge out all your zones and all your loops, whether it's a radiant system or a panel radiator baseboard, it's pretty easy to get dirt out of a new system. But when you start doing these retrofits where they're tying into old piping, maybe old steel piping, or they're trying to use some old radiators and stuff, I think it's critical that you have a good dirt remover that stays in there and is at a good quality that can take out very small particles and just keep working over and over. And that's why, we like to promote the a dirt separator as opposed to a Y-string like our disc cal. And our dirt cals specifically for dirt removal, and it'll take a small size and it keeps working, and it actually traps whatever it pulls out of the system into a little container at the bottom that you can blow off with a hose or with a little ball valve that we give you on the bottom. So, I mean, there's never a bad time to use a dirt separator. What we are starting to do at Caleffi is starting to put some combined product out on the market. So now instead of having to buy an air elimination device and a dirt elimination device, we're putting those together in one package. So now you can get both air and dirt separation out of one device. So it makes it a little bit more affordable for you and for your customer, as well as a little bit easier piping where you don't have to pipe two separate components, and you can get kind of two birds with one stone.
I guess we're almost out of time here. I'll make a comment that we're not answering in this webinar, and we also got similar questions in our other geo webinars, and that's in the area of sizing, along the lines of sizing is oftentimes a problem in geothermal applications, sizing loop fields, and basically questions in terms of how do you do the sizing, and we'll collectively be offering a webinar on sizing. And I think we've talked about sources that address that issue with various programs and what have you, but is it something that we're looking to address in any time future?
Yeah, and to be honest with you, I don't know that much about the geosizing. I am signed up to start taking some classes and learn some more. We're going down to the IGSPA conference here in Tulsa in a couple weeks, and I'm going to take some classes there. Some of the various manufacturers have some classes going on, so I need to bone up on that myself. Again, Caleffi's contribution to this whole thing is what we know from our hydronic side. We're good on the load side. We don't know that much about the loop fields as far as sizing and stuff like that. We want to offer some components, but we need to learn a little bit more about that. But, I mean, that's going to certainly be a site-specific detail. I mean, the ground varies if you're going to use loops, if you're going to use wells, if you're going to use a pond. I mean, that's something that, that needs to be paid attention to. That's a critical. That seems to be the place where that makes or breaks the geo system is, the amount of care and the amount of attention given to sizing those and get them installed properly.
Okay, Bob, those were all the quick questions. I think the other ones you can address, so thank you very much.
Well, yeah, and thanks everybody for joining in. Again, stay tuned for the next webinar with Dan Foley and then our solar one after that, and we'll see what we come up with our show and tell series. And thanks everybody for joining in. Bye-bye.